The last half will be recorded. Just took a shot at some passwords. How's that? They were very creative. Don't tell me, but it's U of Minnesota, U of MM. Okay. Well, so I was looking at emulsifiers. So what do we need in the beverage? Well, we need water, obviously. Okay. Then we need some kind of an emulsifier. And very commonly, that is a hydrocolloid, a food hydrocolloid. Gum acacia works in that category. There are some chemically modified starches that are designed for beverages as well. And, of course, the hydrocolloids do give part viscosity in the concentrate, not in the finished beverage. So they're fairly stable beverage concentrates because they do have density, they've got viscosity, they have a number of things going for you. The hydrocolloids, of course, have to be soluble in water, and they are low viscosity. Gum acacia fits in that category. Gum acacia is very unique in terms of a low viscosity. It's a good emulsifier, doesn't gel. So, again, meets many of these needs. Talked about gum acacia when we were talking about spray drying systems. So already have a pretty good idea of that. It is a very traditional material, natural in all countries, which is really a plus. Structure, it's a glycoprotein, so that's what makes this emulsification. To be an emulsifier, you need something that has a hydrophobic and hydrophilic end to it. So we need both ends because they can be at the interface, reduce surface tension, stabilize the system. So that protein is what makes it an emulsifying carbohydrate, really. Functional, it's very good. It's not exceptional. The modified starches tend to outperform it in many ways because they're designed for this purpose. Man made them as opposed to what nature provided. So they're good. They do the job. 90% in beverages is Senegal, 10% is the Sayal. Again, it depends upon where the market's going these days. A low viscosity, 30% solution is only 100 centipoise viscosity. So again, you can have very concentrated beverages. Very stable, under pH is 4.6 to 5.5, which covers not all of our beverages because our beverages go down to about 2.5 if you get into the colas. It's HLB of 8 to 11, so again, it's functional for us. The alternative, like I said, tends to be modified food starches, not natural. They're OSAN, octylsuccinic anhydride derivatized starches. So just exactly the same product, or very, very similar, I should say, to the product that's used for encapsulation. It's same limits for OSAN substitution, so it's limited how many of those OSAN groups you can put on hydrolyzed starch by law. Clean substance, remember gum acacia, it's harvested some plantations, but a lot of it has just come in from various people in the region, Africa, Central Africa, and it's sold as a commodity. So you get a lot of sticks, rocks, all kinds of interesting things in it, so it has to be cleaned up, where modified starches don't need that kind of cleanup. No supply issues, made from cornstarch. Gets you away from political issues, weather issues, all kinds of issues related with getting a product from Central Africa. Slightly cheaper than acacia. Unstable and alcoholic beverages greater than 6% alcohol. And so we do have, of course, a number of flavored alcohols, and they get fairly high levels of alcohol, and they wouldn't function particularly well in those products. So the modified starches don't. Beverages, see, like I say, they'll run. Yeah.
Do you know why they're unstable?
I haven't ever noticed why. Whether it's solubility, function, I have no idea. You wouldn't think it would be a problem. They're not electrically charged. And so that's one factor. No idea. pH ranges from 2.5 to 5.5, and colas are on one end of that, cream sodas on the other end, in the 5.5 region. Taste, microbial inhibition, so there's always an acid taste, generally an acid taste in the beverage, so that gets you the low pH. And of course, low pH tends to give you a good deal of microbial protection as well, or pathogen protection as well. So tend to keep in that acid region. Citric acid is the most common stimulant that's used for this. It does enhance citrus-based beverages and chelates trace metals, which minimizes oxidation of essential oils. So acidity certainly suits many or several different roles. Preservative, sodium benzoate is the most common preservative that's added to beverages. It's interesting that there is an order of addition when you put sodium benzoate into a product. You must dissolve the sodium benzoate first in the liquid, the water that's used, and then you drop the pH. So you have to add your benzoate first. The sodium benzoate is soluble, and then you add your citric acid, which normally I say citric acid, and drop your pH. You will not disperse sodium benzoate in an acidified product. You must disperse it first and then drop the pH of the product. And if you've ever had too much sodium benzoate, it really gives you biting back in the throat. It's not a pleasant contributor flavor. Preparation of beverage emulsion. Prepare an oil and water phases separately. So you take the water, add your sugar, whatever else you want in there, citric acid, coloring, hydrocolloid, and so on. Then you take your oil separately, add the primarily weighing agent to the flavoring material. Make a primary emulsion, a coarse emulsion, high shear mixer, homogenize with a high energy system, typically your high pressure piston homogenizer. And you want to get down around 1 micron. And with that 1-2 microns gives you a pretty stable product with the weighing agent in it. If it weren't for the weighing agent, you'd never be stable. So a typical beverage, so this is the emulsion that the beverage manufacturer sends to all of the bottlers. They dilute that 50-fold into a sugar syrup. They take that sugar syrup and dilute it 1 to 5 to make a finished beverage. And that's a normal dilution, the way it's done in the bottle industry. And it's interesting that if you would not add this emulsion to the syrup, you would not get a clear beverage. And so that has to be done also. You cannot add this directly to the beverage. You need a sugar syrup here. Sugar makes that water a little more nonpolar. Sucrose in solution makes it more nonpolar. And so you can actually get this more or less dissolved in the syrup and be able much more of a challenge to get into the beverage. You start looking at low calorie, no calorie, you end up having to deal with this differently in formulation to be able to make this happen. If you're looking at dry mix, well, that's pretty easy. You spray dry emulsion, you simply dilute it with water or sugar, whatever you want. You asked about the stability. Is this stable? Well, problematic. It is a metastable system. Stable for the moment, it isn't going to be stable over time. And so we simply can't add enough weighing agent. So if we would go ahead and do a 50% estradiol, 50% vegetable oil, use that at 100 parts per million, the legal maximum, you end up with a specific gravity of 1.02. That's what I gave as an example in that Pearson square chart. Why did you target 102? Specific gravity 102. That imparts the maximum estradiol that you can use in that product. The orange terpenes are a little lighter than vegetable oil. And so our orange terpenes are around the 0.8, 0.85, someplace in there, specific gravity. Vegetable oil, of course, is probably 0.9 or a little heavier. So if we were going to make a cloud emulsion and orange terpenes, so we can do a cloud either way. Use this as a particulate phase or this. If you use this as the particulate phase to make a cloud, the maximum we're going to get is specific gravity 0.97. So this system is going to be a less stable system than this system.
Earlier you mentioned that estrogen is difficult to dissolve in essential oils.
Mm-hmm.
Does vegetable oil help to dissolve estrogen?
It's more soluble in vegetable oil than it is in terpenes.
Okay.
But it's still a pain in the butt.
The terpenes will dissolve in vegetable oil, right?
Yeah. Or the estrogen will dissolve in orange terpenes. Yeah. That's primarily limonene. You know, when you go through all the extractions, you put lemon oil into alcohol water, you get this beautiful, lemon extract that's soluble. Where do those terpenes go? One of the places they go is to make up this cloud emulsion. So the beverages makes it. The beverage companies make it and use it. So, yep, there's certainly a problem with physical stability. It does have a somewhat limited shelf life. Interesting, it's easier to make a cola stable than it is any of your other beverages. And that's primarily because you use some caramel color. And that caramel color is also an emulsifier. And so you get a kind of a double whammy for emulsifier in colas from the caramel color, and you get it from the gum acacia. So you got two things going for you. Chemical stability. We do have flavor changes over time. I don't know if any of you have ever had a cola beverage that's been sitting in a gas station too long in the window of a gas station. They can get pretty ugly if they're beyond normal shelf life. And so you get hydrolysis of flavorings, acid catalyzed degradation of the terpenes, and so they have a shelf life, not only physically in terms of emulsion, but in terms of flavor of the system. Emulsion shelf life. Okay, so flocculation typically isn't a problem. You remember the ways they destabilize? They will come together. If you've got individual particles, they don't rise too quickly. But if you start getting them flocculating, sticking together, then they rise more quickly. So they rise together once they stick together. So the idea of flocculating is something that's worried about a great deal. And that's usually not a problem with beverage systems. It is in some other systems. Maybe you're mixing the incompatible ingredients, high ionic spin, which we might look on some health beverages where you've got a lot of salts and whatever. But normally in normal beverages, physical, diet beverages, typically not a problem. Creaming is more of importance, and that comes from they have done a good job in homogenization. So again, this should be kept in check by good homogenization. Here, like I say, looking at formulation and what you're delivering for meals and so on. And so particle growth in these beverages is probably primarily due to Oswald ripening. And so we'll spend a little time with Oswald ripening. So, they say you look at any emulsion or what you learn from any emulsion studies, they certainly all apply to this. Small particles, viscosity, and so on. This was something we did a while ago. And it's always interesting to look at what's on the market and look at market claims. What do manufacturers claim? Oh, this is superior to that. Oh, is it really? And so we went out and got 1, 2, 3. Well, I don't know if that's exactly right because we got a couple of concentrations. And so we picked the common commercial products. And there's a couple of these products that are claimed that this is designed for beverages, and therefore this one's better than some of the other ones. And so we tried it at its usage level. The manufacturer said 7%. Kind of the standard is 16%. So we cut it down to what the manufacturer says it's still perform. The same for this particular product. So the different manufacturers Here's modified starch, modified starch, modified starch, modified starch. So again, modified starches and gum applications. And looking then at the mean droplet diameter. So again, the smaller the particle to a point, the more stable that is. And all the gum applications really performed very well. This is PG2000 is designed, a modified starch designed for beverages, and that did pretty well. You look at some of the other ones, they didn't perform nearly as well. So gamification does a nice job in terms of an emulsifier. We also looked at clouds and looking at orange terpenes. So can we use an orange terpene cloud or make it out of vegetable oil instead? And beverages based on orange terpenes gave us smaller particle sizes, which would give us a little more turbidity and a little more shelf life stability. Gummification, modified gummifications, there's a chemically modified gummification. And they were better than the other materials. So it's always interesting to get some products on the market and take a look at them. So,
can smaller particle size lead to like faster rates of oxidation?
You know, the oxidation tends not to be a problem. Acid promoted degradation is more of a problem, the low pH of the beverage, because they're typically in a can. There's CO2. You know, there isn't much oxygen that's sealed up in that, so it's typically not a problem. It's degradation from heat or acid. So these are some formulations. So a lemon beverage mix. So lemon oil. Go ahead and add your BBO, estragon, SCID, whatever you want to do the weighing of it. Sugar syrup, so 32 bricks, 32% salt sugar solution. Acacia, equal amount, yellow number 5, so this is obviously lemons, that's the color. Sodium benzoate, that's preservative. Citric acid adds acidulant. Water to make up to 1 gallon. So 8 ounces of lemon oil blend mix here makes 1 gallon of finished concentrate. So the bottler's syrup is what it's called. Animal feed compositions. It's kind of interesting that we do flavor animal feeds. The idea is that if the cow likes the feed, well, they'll eat a little more feed, maybe they'll get a little more milk or a little more weight gain. Needless to say, the flavors aren't very sophisticated, and the cow doesn't do too much, or the pig, whatever, it doesn't do too much discrimination. There's typically one component. It can be vanilla, as an example, maybe licorice, so a single component flavoring. So not much discrimination. And so here we got a large amount of water, acacia, sugar, and flavor. So that would be the emulsion that's used, diluted in the farm place. Baker's emulsion. So here we got, again, hydrocolloid to provide viscosity, gummification to give us some viscosity, but more so. It's in there for emulsification. Citrus oil, benzoate for preservative and acidity in water. So this is viscous enough so that it'll work into a batter or dough. If you've ever poured water into something viscous, the water runs around. If it's about as viscous as what you put it in, it will tend to mix in. So the whole idea is to make that viscous like a batter or dough so it's easier mixed.
So if we compare the first two formulations to this one, the other one have like a 1-to-1 parts of emulsifier and essential oil flavor. This one has significantly less emulsifier. And I know we don't want a liquid formulation, but my question is now that you change those parts of emulsifier and oil phase, will this emulsion still offer any type of protection to heat or volatility?
No. They don't. You know, so will it perform better in a baking application? No. Because it's really the viscosity and the environment. So this is a small part of the formulation. It doesn't change the overall behavior.
And the same applies to the beverage emulsions. They won't provide any type of protection.
No, they get dispersed and any effects they had, as a concentrate, they're completely lost in the application. Microemulsion, so if you're into mouthwashes, you go and pick it up from whoever. Quite an interesting formula. Acetylpyridinium chloride at 0.1%, some citric acid to acidify. You got to get some peppermint, eucalyptus, clove, and then a good allotment of surfactant again. 10% alcohol to aid in solubility and act as a preservative. And then a sorbitol, so some sugar to give it, sorbitol it is a sugar and it isn't a sugar. Again, it changes that system somewhat. It gives a little different texture to it, mouthfeel, and so on. And then make it up to 100 parts. So what we're doing here is we're just changing the system to not some really strong surfactants. And put that with alcohol and sorbitol, they tend to be soluble more so than an emulsion. You pretty much solubilize these things. And that's where they get their high intensity flavor from. They get the flavor to cover up your acetylpyridinium chloride and these other things that are kind of obnoxious in taste. So you get a pretty good shot of flavor just to cover up the surfactants in that. And of course, the industry would like to get rid of those surfactants and be able to flavor them more or less normally. Emulsifier, how much is needed to solubilize 1 gram of oil? Well, if you're going to disperse methyl salicylate in that past solution, you'd have to have 1 part of emulsifier to 9 parts of methyl salicylate. So 10% is going to be the emulsifier of tween 20. If you're using tween 80, you've got almost 20% almost for tween. So you're tying 10 to 20% emulsifier, or surfactant, I should say, in these mouthwashes. And different materials have different solubility, so you get by with different levels of surfactant in them. Pickle emulsion, just in case you're into pickles. Here's a recipe for you. Dillweed oil, 58 ounces, little oleoyl resin, capsaicin, capsicum, so get a little bite to it. Pimenta, laurel leaf, cassia. Here's our polysorbate surfactant again, propylene glycol, and then water, if there's any room for water in that formula. And it actually makes that a really, really fine emulsion that tends to be absorbed into the pickle. Like, how do you evaluate an emulsion? Is it going to be a problem? Again, there's many different approaches to that. Some of them are simply visual. So again, look at the emulsion. Take a look at it under a microscope. Are the droplets small? Are they uniform? Is there a black ring around those droplets? And so there's some air that tends to get incorporated. Undissolved fibrous-looking crystalline material that comes from the gum that's used. Satellites of air on the droplets, chains, clusters, aggregates, and so on. So actually looking at it has merit. Typically you'll run a particle size as well, but there's merit in simply observing what's it look like, what are its properties. If you want to give it a little bit of time, okay, you centrifuge it, rather than give it a lot of time and let it sit there for some weeks. How's that? So you can centrifuge the emulsion. What are you doing? You're increasing the g-forces, the gravitational force in that equation. And so basically you look for creaming. You centrifuge for so many minutes, it's off the cheese. Is there a cream layer? Is there a sediment? And if there is, that sediment's rather concerning because it really shouldn't be there. It should cream. Look for breaking of the cream. Again, so is it partially separated, complete? And again, like I say, do particle size, dilute it, and run turbidity testing. There's some fairly nice equipment out there to measure the turbidity, the appearance, the cloudiness of solutions. You can put them under a microscope, take a look at it, pick up a beverage and let stand looking for a ring. And that's very traditionally done by putting the beverage into a 1 liter bottle and lay it on its side in the sunlight so you can see it fade and see it separate. So it's laid on its side in a large bottle because there's always a little bit of trapped air, and so that trapped air is right at the middle of the bottle. It's easy to see. Look for film on top of the emulsion, dehydration layer. Look for film on the surface of the beverage. Check opacity of the beverage, shine a light through it. There's all kinds of different ways that different companies look at these things. Depends upon your sophistication, depends upon how much money you have. If you've got a lot of money, you'll have some sophistication. If you don't have a lot of money, you'll be looking at it with a flashlight and whatever else happens to be. Let you change your mind. Okay. The more viscous emulsions, you just let them expand, look for syneresis, separation, centrifugation, and so on. Microemulsions, do it with water, look for clarity. And so you think about that microemulsion where you have all these surfactants, alcohol, you dilute it a little bit, you're putting some stress on it. You're diluting the surfactants, you're diluting the alcohol. And so basically just some dilution does it. Nobody likes to do shelf life testing. That's a pain in the butt. It takes a lot of time, and usually you want to have your product out in the marketplace or sold by the time you'd be getting results of these things. So this used to be done much less done today. Just make up a beverage and look and see what happens to it over time. So that's kind of that for flavor emulsions. We'll just spend a few minutes, and it won't be a lot of time, looking at nanoemulsions. Nanoemulsions are interesting, and I have a little bit of a problem with what's done not in the industry, what's done in the scientific journals. People will really expand nanoemulsions in size. I've reviewed a paper yesterday where they said 300 nanometers was a nanoemulsion. I said, not to me. You've got to get down, in my opinion, down to 100 nanometers, because really at 0.3, that's a fine emulsion. That's not a nanoemulsion. And so, but putting nano in the title of a paper gives it prestige, and we're doing something unique. So it's it's actually an abused term these days because it's supposed to do magic for you. Characteristics like submicron, if you do well enough, it's optically transparent. It's a low surfactant to oil ratio, high specific surface area, over 30 square meters per gram of your oil. This is where are they? Well, possibly in some beverages, power beverages. Actually, it's fairly good data that says nanoemulsions are absorbed better in digestion. So if you're going to deliver a drug, a pharmaceutical product, there's an advantage from that standpoint. But like mouthwashes, I mentioned, any place where you want a clear product, it's attractive because it certainly is stable to cream. And so there's some advantages to it. These are some images of, this is a 98 nanometer, 351 nanometers, 726 nanometers. And this is getting clear. It's still not clear. It's gonna be gray. So you have to get under 50 nanometers before you're going to get a clear product out of that. And that's your goal. Clear is your goal. And it's done in the usual way. Oil and water, make a primary coarse emulsion, and then go ahead and make a fine emulsion out of it. There's no class here, so this is the amount of pressure that it takes to reduce your particle size. So this is your target droplet radius. This is the surface tension and the pressure you must apply. So these two are given from the system, and that gives you the pressure. And so we work with this range with microfluidizer, 23,000 psi, and that's a picture of our microfluidizer that we use. For turbidity, So we were working actually with medium chain triglycerides, and we're working with orange terpenes. And so this is kind of looking at what kind of particle size in terms of nanometers. And it takes a good deal of work to get down below this, maybe 125, 150. It takes tough work to get into that region at all. Certainly, type of emulsifier is important. And here's where really fine or small molecular weight emulsifiers are really helpful. It's really hard to get them with any food polymer. And food polymers are what we use. We want it natural. It's really tough to do that. So things like Tween are very good in particular. Also, sodium lauryl sulfate is another one. So some of those actually work quite well, small enough to cover that surface and then protect it and get to it quickly to protect it from coalescence. And so, again, looking at different systems, maybe we also medium chain triglyceride with different types of emulsifiers and try to get that particle size down. The instability systems, they're really too small to cream. They're not going to cream. Your biggest particles, well, if you left them long enough, but you really want them sold and consumed well before that happens. And so what happens to them is they do undergo Oswald ripening. Like I said before, these tiny particles, tremendous high energy. That's not a stable system. And so your small particles tend to diffuse into the continuous phase water and move to the big particles, much, much lower energy. The interesting thing is that your particulate phase, is important because these materials have to migrate through water. So these are your particles. Is it a vegetable oil or is it an essential oil? Essential oils have some water solubility. So they will move from small particles to big particles. But if you make any emulsion, not emulsion based on vegetable oil, your triglycerides don't go in water. So nanoemulsions based on essential oils have limited life due to Oswald ripening. If they're based on vegetable oil, then they're much, much more stable. And very commonly, what's done when you want to make these is you'll actually use the combination. So your vegetable oils need a good solvent for your essential oil, so there's less driving force. It really doesn't want to go anyplace. It's kind of happy there. And so using a combination, your essential oil is your flavor. So it tend to keep your flavor in the droplets, small droplets, and not let it go into the larger droplets. You know, the future of these things in the food industry, I think, is interesting. I don't know, some of you are from the industry. Do you ever deal with nanoemulsions? That topic ever come up for you? Is that of interest? No. It is problematic just because we don't have natural emulsifiers for it, and everybody wants to put a natural label on it. And it's about impossible to do that. And so the idea of your emulsification, or I shouldn't say emulsification, but your homogenization, that can be problematic because you need something that gives really fine particles but in large volume. They're fairly expensive then to get into that ballpark of equipment. And there's some public opinion. I don't know what your public opinion is if you say nanoemulsions, are they good or are they bad? There's a certain opinion. Nanoemulsions are small enough to cross the blood-brain barrier, and whatever you put into that beverage can get someplace it hasn't traditionally gone, and so that raises some issues. I don't know how public that is or how many people believe in that, but when you talk to people sometimes they say, no, we're not interested in nanoemulsions. No, that's nice, but we're not interested, primarily for that reason. Well, wouldn't you know, we finished up early again. I got to work at that. Anyway, but anyway, let's call it quits. And so next week we will have class and we will have a lab, and it'll be on applications. Good. Whitey's already started this thing spoiling for our offsite cloud. So he's working maybe bad tasting things.